Okay, let's go ahead and get started. One just brief administrative announcement. So next Friday I'm actually out of town. So I was thinking that instead of finding an alternate lecturer, I would just schedule a makeup lecture the following Monday. Does anyone have a problem with that? Having no class next Friday, whatever date that is. Friday, October 12th. And then a makeup class on Monday, which would be October 15, maybe? Is there anyone for whom that's a problem? It's a problem for you? Is it? I mean, I record the lectures anyway, so I'm sorry about that. It seems like if it's okay for all but one person, then maybe that's the best way to proceed. And I record the lectures anyway, so hopefully that won't be the end of the world. Okay, but now let's go ahead and do some physics. Very, very excited about what we're doing today. So today I'm going to discuss entanglement, which is, of course, something that you have already encountered previously in your lives as physicists. But today, I'd like to introduce it a little more systematically and describe to you exactly why it is that entanglement is so closely related to the topics in quantum statistical mechanics that we introduced last class. So let me just remind you of what we studied last class. So we saw that if we have incomplete information about a system, about, say, the state of a quantum system, then the state is described by a density matrix or a density operator typically denoted rho. And if this density operator rho is the quantum mechanical operator, that is the quantum version of the classical observable, that is the probability density, rho of x and p, that would describe the probability that the system is in a state with a given x and a given p. So quantum mechanically, just as with any other operator, any other observable, it turns into a Hermitian operator. And in particular, if we have an ensemble of states such that the system is in a definite pure state every time you perform a measurement, but we just don't know what that pure state is, so that we would say the system is in state, say, alpha I, where I is an index that labels some subset of states in the Hilbert space, with probability pi, then the density matrix corresponding to that is the sum over I, pi, times the projection operator on to the state alpha I. And the rule that you use for calculating observables in this ensemble of states is that the expectation value of some observable A, if you compute not just the quantum expectation value, but you average over many measurements of states drawn from this ensemble, is the trace of A times rho. And what we sought at the end of class last time was some measure of the amount of ignorance that we have about the quantum state of the system, which is to say we sought some functional S that would depend on the density matrix and would tell us how ignorant we were about the state. And we decided that in order to have a reasonable definition for S, it should be additive if you have multiple quantum systems that are not interacting. So S of a system A plus B should be S of A plus S of B. And in order to do that, in order to formulate that precisely, we'll need to understand exactly how it is we treat multiple systems in quantum mechanics. So how to describe multiple quantum systems. Okay. So let's first think classically for a minute. So classically, given two systems A and B, then if you want to consider the joint system, which is A union B, then the state of the system is a point in the product of the two Hilbert spaces. So, if you, just to be a little more explicit, if the phase space of system A is the set of positions and momenta, say, of a particle in the x direction, and the phase space of system B is the position and momentum of a particle in the y direction, then if you want to describe a particle moving in the xy plane, you take the product of those two phase spaces to obtain the four-dimensional phase space, and a point in that phase space will then label the system as being in a state with definite xy position and xy momentum. And so that would be the first statement, the statement about the kinematics of multiple systems in classical physics. And the dynamics is determined by the Hamiltonian, which is the statement that if the systems are non-interacting, the dynamics is determined by the Hamiltonian H total, which is HA plus HB. So if there's no magnetic field or something like that, which would mix up the x and the y dynamics of the particle, then you would just have the Hamiltonian for the x direction plus the Hamiltonian for the y direction. Okay, so these are really two postulates, one or two statements in classical physics, one about the kinematics and one about the dynamics of how you form the description of multiple systems given the individual descriptions of the two systems. So how does this work in quantum mechanics? In quantum mechanics, if we have two systems, A and B, whose states live in Hilbert spaces, let's call them H sub A and H sub B, and the dynamics is described by some Hamiltonians, let's call them H sub A and H sub B. I guess it's really unfortunate that I use the same symbol for Hilbert space and Hamiltonian, but I try and make my Hilbert spaces curly and my Hamiltonian straight H's. Then the analogs of those two classical postulates are that the state of the system is described by a ray in the Hilbert space HA times HB. Where that funny symbol, let me draw it a little more clearly for you, which is a cross contained in a circle, denotes the tensor product of those two Hilbert spaces. Now, you know what a tensor product is, but you may not know that you know what a tensor product is. So let me explain to you why it is you know what you know that a tensor product is. Sorry, that sentence didn't make much sense. So what do I mean when I write down this tensor product? So let's imagine that we have these two Hilbert spaces, HA and HB, and let's just choose some basis of states for those two Hilbert spaces. So let's let the state AI, where I is some index, and Bj, where j is some index, form complete bases for the Hilbert spaces HA and HB, respectively. Then the tensor product of the two Hilbert spaces, HA times HB, is the Hilbert space formed by arbitrary linear combinations, or let me say the Hilbert space of arbitrary linear combinations of the following basis states: AI times Bj for all values of I and j. So that may or may not have cleared anything up for you. What do I mean when I make this statement? Well, if you have two Hilbert spaces, which have some basis states AI and Bj, then the Hilbert spaces of HA is the set of all linear combinations of the A's, and the Hilbert space HB is the set of all linear combinations of the B's. So how do we define the tensor product? We just consider the set of all states, we consider a set of basis states, which are of the form alpha A times B, where we put this symbol here. This is just some sort of formal nonsense. Okay. The symbol doesn't really mean anything. It just means that I'm defining a set of basis states, one for each choice of alpha and beta. And the number of such basis states is the dimension of HA times the dimension of HB. And then I form my Hilbert space, which is the tensor product, by building up all possible linear combinations of these guys. So sometimes we abbreviate AI tensor Bj as just the product state without the tensor product symbol, or even we just put AI and Bj both to live inside the same cat. That's the notation that you presumably are a bit more familiar with. And the important thing to note is that in classical physics, the dimension of the product of the two phase spaces is the sum of the dimensions of the individual phase spaces. But the dimension of the Hilbert space of the combined system given by the tensor product is the product of the dimensions of the individual Hilbert spaces. You get one basis element for your tensor product Hilbert space for each pair of basis elements of the individual Hilbert spaces. And so, and in particular, you can form an arbitrary linear combination for any pair. That's the linear superposition principle of quantum mechanics. So because of linearity, or because of quantum superpositions, we have a vast increase in the number of states. Increase in the number of states in quantum mechanics. So let me give you a very simple but loaded example of how this might work. So let's say that I have a computer whose memory consists of a bunch of bits. Okay. What is a bit? A bit is a system which can take one of two possible states. Then how many pieces of data do you need in order to write down the state of a system consisting of n bits in classical physics? Okay. Well, you need n bits. But in quantum mechanics, you need 2 to the n pieces of data. Or, to say that a little bit more succinctly, let's consider a 2-state quantum system. Then the number of pieces of information that you need in order to uniquely specify the state of the system of the n-fold tensor product of 2-state systems is 2n pieces of data, because the dimension of the Hilbert space grows exponentially in the number of bits. That's why computation is so much more powerful. That's why quantum computers are so much more powerful than classical computers. Because if you're clever, you can use that exponential growth in the number of states available and in the amount of information that you can encode in a quantum state in order to do computations very, very quickly. So the art of quantum computation, which is something that we won't really get into in this course, is the art of cleverly encoding the computation you want to try and perform in entanglements in this vast Hilbert space, and figuring out how to process those entanglements properly. It's a very interesting subject. So, I should mention that a lot of the confusion that comes when we start thinking about tensor products is coming from not being quite sure what to do with things like that funny X inside a circle symbol that I use to denote a tensor product. And the rule that you want to remember is that you just should sort of close your eyes and follow your nose. So, for example, the dual, the inner product, and all those other nice structures on the tensor product Hilbert space are inherited from those structures on HA and HB individually. So, for example, the dual of the state AI tensor BJ is the state AI bra tensor BJ bra. And the inner product between a state and the tensor product is found by simply using linearity and taking the tensor product between the individual HA and HB states. So, as I emphasize, this is certainly something that you have seen before. You might just not have thought about it in quite as much detail as we're going to do today. So just to give you an example, let's say that we want to study a particle moving in 3 dimensions with spin 1/2. Then the Hilbert space is the Hilbert space of a particle moving in 3 dimensions, tensored with the 2-state system that describes a spin 1/2 particle just pinned to the origin. Question?
That tensor product, is it commute? So it's A?
Yes.
Tensor, no.
Okay. But, I mean, the tensor product, if you want to think about it that way, commutes, but there's no reason why you would ever need to worry about changing the order between the 2 sides. But yes, it commutes. You know, I could spend a long time doing some slightly boring formal mathematical manipulations where I tell you exactly, you know, where we work all that out explicitly. But really, you just need to follow your nose. Okay. I'm gonna go through some examples now where we'll understand exactly how that works. But for example, the spin 1/2 particle moving in 3 dimensions is a great example. What is that Hilbert space? Well, it's the Hilbert space whose basis is given by a set of ket vectors that have 2 labels. One of the label is the x position of the particle, and the other is the spin of the particle, which would be either up or down. Now, you ask the question, does the tensor product commute? Well, yeah, it commutes in the sense that if I wanted to, I could reorder my labels. I could write S first instead of X. Is that a useful thing to do or an interesting thing to do? In this context, not particularly. There might be other contexts where it's worth thinking about. For example, when considering multiple identical particles, the tensor product of two bosons is going to be, well, we'll burn that bridge when we come to it, but we'll have interesting things to say about the symmetrization properties of the states in the Hilbert space for bosons versus fermions. But in a formal way, you could certainly say that the tensor product commutes. In that the two Hilbert spaces that you would define by taking the tensor product in alternate orders are isomorphic. Okay. Or isomorphic is another one of those formal words that doesn't mean very much, unless you happen to care about what it means. Any other questions? Isomorphic is the fancy word for equals in mathematics. Okay. Now, we don't care just about Hilbert spaces, we care about observables. And in particular, we care about operators. And so we can form an operator on the tensor product Hilbert space from a pair of operators, A and B, which act on HA and HB. So, in particular, if you have a pair of operators A and B that act on the Hilbert spaces HA and HB, then we define their action on the tensor product Hilbert space by defining its action on the basis vectors of the tensor product Hilbert space. The basis vectors are these formal products, and we define the action in the obvious way, exactly as how you would define it if you didn't think very hard and you just kind of ignored that tensor product symbol. And if we have an operator that acts just on A, it can be extended to an operator on the tensor products Hilbert space simply by tensoring it with the operator 1, which is an extremely fancy way of saying that it just doesn't act on the B Hilbert space, where 1 is the identity operator on the B Hilbert space. So this is the kinematics of multiple quantum systems. We also want to talk about the dynamics of multiple quantum systems. And if two systems are not interacting, then the dynamics on the tensor product is very simple to write down. It's just given by the Hamiltonian, which is the sum of the two Hamiltonians, HA plus HB, just as in classical mechanics, where in writing down that formula I've been a tad sloppy here. I should really, I suppose, write it as HA tensor the identity operator on B plus the identity operator on A tensored with HB. But, of course, the identity operator doesn't do very much. Okay, so I could just write it as HA plus HB, provided I remember that HA acts on A and HB acts on B only. So, there's one point that I should make here, which is an important point, which is that there are really two different ways that you could imagine combining two Hilbert spaces together in order to form another Hilbert space. And it's important to keep in our minds the distinction between these two different ways. So there's the way that I have defined above, which is the tensor product. And there's a second and quite distinct way, which is known as the direct sum. And that's denoted with a plus inside a circle instead of a times inside a circle, where the direct sum is the Hilbert space spanned by linear combinations of the basis vectors which are given by the basis vectors of hi, or I suppose, let me write it a little more formally, by the union of the set of basis vectors of ha with those of hb. So, for example, if you have two state systems, then you could define a Hilbert space whose basis vectors are the union of the basis vectors of the first two-state system and the second two-state system. That would be a four-dimensional Hilbert space, but it would be quite different from the four-dimensional Hilbert space, which is the tensor product between the two. Okay. And so the dimension of the direct sum is the sum of the dimensions of the two individual Hilbert spaces. And when you think about vector spaces and linear algebra, very often in your head, you're often imagining a direct sum, not a tensor product. Tensor products are a little harder to visualize. Let me say another sentence which will make it a little bit more clear exactly what I mean by the direct sum. So if you have an operator A that acts on HA, then it will act on the direct sum Hilbert space by an operator which is easiest to think about if you think about it in block diagonal form. So the Hilbert space, which is the direct sum of HA and HB, is the Hilbert space which you would get if you just thought about these as vector spaces. It's just the what people call the Cartesian product sometimes of these two vector spaces. Namely, if you have an n, if A is an n-dimensional vector space and B is an m-dimensional vector space, then you have the n plus m-dimensional vector space that you could summarize in terms of column vectors with n plus m components, if you like. The first n components would be the coordinates of a vector in HA. The last m components would be the coordinates of a vector in HB. And operators could be formed by writing them in block diagonal form, where the first n by n block would be some operator acting on HA. The last m by m block in the lower right-hand corner would be something acting on HB. And then you would have some n by m or m by n dimensional rectangular matrices in the upper right and lower left-hand corners. So in your head, when you think about combining vector spaces, this is usually what you think about. And the point that is important to remember is that this is not a tensor product. This is something much simpler in some ways. Okay. Yes?
So if you were to take, for example, L squared and LZ, what would be the difference between getting a tensor product of those two or a direct sum?
L squared is what? What do you mean? Okay. Tensor product is, I guess I don't know quite what you mean. Okay. You take a tensor product of Hilbert spaces or of states. Not of operators. Well, rather, so L squared is an operator that acts on the Hilbert space of, say, a spin 1/2 particle. And LZ is an operator that acts on the Hilbert space of a spin 1/2 particle. If you had a system describing a pair of spin 1/2 particles, which is the example that I'm going to do in a minute, then, you would have to say there's an LZ that acts on spin 1 and an LZ that acts on spin 2, and you could construct LZ tensor LZ1 tensor LZ2. You could also construct the operator L squared that acts on spin 1, the operator L squared that acts on spin 2. If, for example, the two spins are coupled by a magnetic field, then you often write down an interaction, which is sigma 1 dot sigma 2. Okay, so that would be an example of an operator that acts on the tensor product Hilbert space, H spin 1 tensor H spin 2. That operator would be jx1 dot times jx2 plus jy1 times jy2 plus jz1 times jz2. Yeah, I mean, you guys know all of this stuff. It's just that the language is a little unfamiliar. But I'm introducing this language because, in fact, it's deeply and intimately connected with a lot of things that we're going to want to think about. Yes?
Why is it that we choose the tensor product of the Hilbert spaces and not the direct?
Okay, good question. Why is it? Well, it's sort of forced on you if you think about it. I mean, let's imagine that we have two completely non-interacting systems here. And if I want to describe that's a great question. If you have a state in Hilbert space of system 1 and a state in system 2, then you should be able to describe the combined system by specifying a state in system 1 and a state in system 2. That's all I'm saying. Okay. But the important point here is that because of the linearity of quantum mechanics, you can form many more possible superpositions of this product of Hilbert spaces than you could from just the individual Hilbert spaces. Is that clear? Is that okay? We write down this funny symbol with an X surrounded by a circle, and people suddenly get very excited and they think it's something new and different. But it's not anything new and different. You've been doing it your whole life. Whenever you write down a ket vector with two symbols inside of it instead of one. Okay. Yes.
I guess mathematically I see why they're different. I understand.
Yes.
How do we know, like, experiments that this is the right one? I guess if there are different results, how do we know if this is the right one?
Well, I guess I don't see a clear alternative to this. Okay. Because the alternative would be to consider something like the direct sum. I don't even quite know how to formulate. I know how to formulate it mathematically, I guess you could say, sure. But I don't know physically, all the states in the direct sum don't allow me to put one state in one system and one state in another system. So it would mean that you couldn't just have non-interacting systems that would behave independently. Let's put it this way. We want to develop a formalism for quantum mechanics, which allows me to study, understand, materials physics without solving quantum gravity. Okay, right? Or which would allow me to predict the outcome of an experiment on the Earth without knowing the quantum state of an electron in Alpha Centauri. Okay, right? And that should allow me to put the state here on the Earth in some system and be able to put a state in Alpha Centauri in a system in Alpha Centauri in some state, but I should be able to freely ignore that. But if you think about the direct sum Hilbert space, then you either have a state here in a system here in a state, or you have a state in a system in Alpha Centauri in some state, not both. Okay. So I think it's sort of just forced on you by the requirement of, I would say, locality, or let's say extensivity. Okay. It's a good question. There's a sense in which I really haven't told you anything you don't already know. But I'm using a language that's slightly new and being a little more careful because I'm now about to start telling you things that are going to seem quite surprising. And in fact, that everything entanglement is the same as considering density matrices. Okay. And it's the same as quantum statistical mechanics in some sense. That, I think, is something that is worth thinking about. Other questions? Good. So, I've used the word entanglement, so let me now define it for you a little bit more precisely. So, a state in HA tensor HB of the form A tensor B, where A and B are states in HA and HB respectively, is called unentangled. All other states are called entangled. Now, even though the basis states, as I have defined them, are all unentangled states, most states, in a precise sense, are entangled. In particular, if you imagine thinking about this tensor product Hilbert space, then the dimension of the space of unentangled states is precisely the dimension of HA plus the dimension of HB, which, if these Hilbert spaces have dimensions that are bigger than 2, is going to be much less than the dimension of HA times HB. So what does that mean? Most states are not simple product states, AB, but rather non-trivial superpositions of product states. And this notion of entanglement is very closely related to the notion of a mixed state and a density matrix that we have described last class. Did I use the terminology mixed state last class? Okay. I should have introduced that terminology. Okay, so let me just remind you so that if a system is in a definite quantum state, so that the density matrix is just some projection operator, then the state is referred to as a pure state. But if rho is not a projection operator, we say that the state is mixed. And it turns out that entanglement is very closely related to mixed states. That is to say, states where you have imperfect information about the exact quantum state of a system. To understand why that is, consider the following case. Suppose we have two systems. A and B, and we decide to only measure quantities in the A system. So, for example, we could have our pair of spin 1/2 particles, one on the left, one on the right, let's say I only care to measure, say, the spin in the z direction of the left-hand particle and not of the right-hand particle. So let's further suppose that we are in a pure state, that is to say, a definite quantum state, psi, in the tensor product Hilbert space. Then, if we want to measure only the A system, then we would define some observable, let's call it A, which is an operator that acts only on HA. And then I want to start thinking about the outcome of an observation. That is to say, the expectation value of this observable A in the state psi. So what is the tensor product Hilbert space? Well, it's the Hilbert space whose basis elements are products AI, Bj, excuse me, which means that our state psi can be expanded in this basis in terms of some coefficients psi ij. So the expectation value of our observable A in this pure state, well, if I want to use the language of density matrices, then I would say it's the trace of A times the projection operator onto the state psi, or, of course, because psi is just a pure state, the matrix element of A in that state, which, if I were to write it out explicitly in this basis, would be the following. It would be the sum over I and j of this operator A, and if I wanted to use our language, I would say A tensored with the identity operator on B times this projection operator AIBJ. So that's just writing out this trace a little bit more explicitly. And I can then use my expression for the, well, so then let's rearrange this sum a little bit. Let's use the fact that A only acts on the AIs and not on the Bs. So this is the sum over I of AI A times the sum over J of Bj psi Bj, okay, times AI. Or, if I want to write this a little bit more formally, it's the trace over just the A Hilbert space of A times a density matrix rho, where the density matrix rho is the trace over the B Hilbert space of our pure state projection operator. Let me just pause for a moment to clarify a potential confusion. So in this line up here, when I've written A as a trace, I'm really writing it as a trace over the tensor product Hilbert space, whose basis elements are labeled by pairs of indices I and j. And then what I am noticing is that because A only acts on HA, I could also write it as a trace over the Hilbert space HA of A times some density operator rho. And that density operator rho is found by taking my pure state density matrix and tracing over HB. So if I wanted to write out that pure state density matrix, this density matrix rho in a little bit more detail, I would just plug in my definition for psi up above. So what is that? That'll be the sum, well, I have to sum over j in order to take the trace So, and I'll also have to sum over j twice inside the definition of psi if I expand out this definition at the top. So I'll have to sum over 3 different j primes. So let's call j double prime the guy in the trace. And then let's write out the definition of psi here. What is psi? It's the sum over I and j of psi ij times ai bj times the dual vector, which would be the sum over ij of psi ij star, because when you take the dual, you take a complex conjugate. And I should put some prime indices on these because, well, I don't want to mix up my indices. So of ai prime bj prime, then times bj double prime because of the trace. And then, of course, if I can take my bj's to be an orthogonal basis for my Hilbert space, in which case j prime and j double prime all need to be equal to one another. So that means I could write this as a sum over I and I prime of ai ai prime times the sum over j of psi ij psi star I prime j. What is the important point about this density matrix? This is a mixed state density matrix, not a pure state density matrix. So what does this mean? This means that even though the system is actually in a pure state, if we only measure part of the system, it can appear to be in a mixed state. Remember that a mixed state parameterizes our ignorance of the exact quantum state of the system. So essentially what I'm saying here is that if we have a system built out of 2 subsystems, and we only study expectation values of operators acting on one of the subsystems, then we have incomplete information about the state. And that is completely identical to studying, that means that the results of measurements of HA reflect our incomplete knowledge about the exact state. And the slogan of the operation that I wrote down above is given by this formula here. Okay. So let me just write that down again. So we often denote the density matrix that is obtained by that is used for the computation of expectation values on Hilbert space A as rho sub A. And it's obtained by tracing the full quantum state of the system, given by the pure state density matrix psi, which is the projection operator on psi, over the Hilbert space B. So the words that we would associate to that formula are that if we do not observe system B, we trace over it. To go back to our example that I was talking about earlier of a quantum system describing a spin 1/2 particle here and, say, a spin 1/2 particle in Alpha Centauri, if we wish to perform measurements of the spin 1/2 particle here, but not in Alpha Centauri, then we trace over the Hilbert space describing the spin in Alpha Centauri. Questions? Let me go through an example where this will be made, hopefully, a bit more explicit. Okay. I realize that you're just getting used to the notion of a density matrix. So let me go through a very simple example where this will become a bit more clear. And in fact, it's the example that I just described to you earlier, which is that let's imagine that we have two spin 1/2 systems. So that the tensor product Hilbert space has a basis that is 4-dimensional. So there are 4 basis vectors: up, 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 down, down, up, and down, down. And let's say we only want to observe the first spin. And not the second. So let's consider one example. So let's say that the system, the state of the combined system is in a completely unentangled state. So let's say psi is in the up-up state, where both spins have spin up. Then the density matrix that we obtain by tracing out the second spin. So here I'm using HA to denote the first spin and HB to denote the second spin. Well, it's the trace of this projection operator over the second spin. So if we trace over the second spin, what does that mean? That means that every term in this operator where the second spins are equal to one another, that just turns into a 1. So what do we get? We get that guy. Okay. And so it is a pure state. If psi is unentangled, if the two spins are not entangled, then when you trace out over the second spin, you just get a pure state. Nothing too complicated there. Let's consider a more interesting example. So let's say that psi is 1 over the square root of 2 times up, down, minus down, up. Okay, that's actually a very famous state in physics. It's called the EPR state. If you guys have seen Bell's inequalities, then you've met that state before. But let's just consider it again. So what is the density matrix then, which would describe the state of the system if we only measure spin 1? Well, there's a 1/2 out front. Okay. So it's the trace of HB of up, down, minus down, up, times the corresponding bra vector, which is up, down, minus down, up. Sorry. Or, if you want to write that out completely, that is the sum of 4 terms. So we have up, down times up, down, plus down, up, times down, up. Those are the first times the first term and the last times the last term, plus the 2 cross terms. So that's minus up, down times down, up, minus down, up times up, down. Okay. Hopefully I've got all my up, downs in the right place. So what does the trace do? Well, if the 2 spins in... So what does the trace do? Well, if you have a state where the 2 spins in spin 2 are equal, the trace just gives you a 1. And if the 2 spins in HB are unequal, it gives you a 0. So that means that those first 2 terms just become up, up, plus down, down, and those last 2 terms have the second spin not equal to one another, and so you just get 0. So what does this mean physically? What is this density matrix? This is a density matrix which says that you're either in the state spin up or in the state spin down with equal probability. I.e., there's a 50-50 chance when you perform a measurement of spin 1 of being in spin up or spin down. Call that a density matrix is the sum of the projection operators times the probabilities. So here you have one probability 1/2 of being in either of the 2 states. Any questions on this? Yes.
What would happen if we had 3 spin half systems?
Excellent question. Then life gets even more complicated. In fact, depending on how energetic I am, I may work out an example of 3 spin 1/2 systems next class, because that gives you an excellent thought experiment where you can think about Bell's inequalities actually in a much clearer way, I think, than in the original Bell paper. So I actually may go through a specific example of a highly entangled state of 3 spin 1/2 particles. But yeah, you just do more of this. Okay.
If you have 3 spin 1/2 particles, then we should have 9 basis vectors.
Well, you'll have 8, right? 2 times 2 times 2. You'll have 8 basis vectors. And so there are, it's an 8-dimensional Hilbert space. And the state, if you only measure, and then, I mean, it's kind of, historically speaking, it's kind of remarkable that it was only in the last 2 decades, really, that people began to appreciate just how interesting and confusing quantum entanglement was. And it's really, I mean, there's really a new field of physics, quantum information theory and quantum computing, which is developed, which is essentially understanding and exploiting these various properties of entanglement. So I have to sit down and figure out exactly how much time we have left in this course, but if we do have enough time, then next lecture I'll probably give a lecture on some more details of this. So yeah, it's a fascinating subject. I mean, there are whole courses. You can take a whole course on quantum computing, okay, or on quantum information theory. Good. Other questions? I realize that the computation that I've done here is actually, it's very simple, but it's in a language that you're not quite as familiar with. You're not quite as familiar with the language of density matrices. So it's going to take you a little while to wrap your head around it. On the next problem set, I'll be handing out a lot of cool problems you can do. You'll derive quantum teleportation, which is a very similar effect. Actually very similar to this. And so you'll have a lot of chance to practice your density matrix skills. Okay. Let me make one more comment, which is that this process works even if the initial state in the tensor product is mixed. So let's take the example that we just discussed. Let's say we had 3 spin 1/2 systems, and you choose to focus only on the first 2, so then you trace out over the third spin and you get a density matrix, and then let's say we have that density matrix that I'll call rho AB, the density matrix used for the computation of observables that act on both HA and HB. Then if you have a third observable A that acts only on Hilbert space A, then the expectation value of A, computed with the density matrix rho AB, so I've used the symbol of the expectation value with rho AB as a subscript, by which I mean just the trace of rho AB times A. What is that? That's the trace where the trace is over the Hilbert space HA times HB. Let me write that out a little bit more explicitly. What is that? Well, if my operator A only acts on HA, that's the trace over HA of rho A times A, where rho A is the trace over HB of rho AB. And this is sometimes referred to as the reduced density matrix. You take a full density matrix describing an ensemble of states in the full combination system A and B, and you reduce it by tracing over B to describe the density matrix that you would use to compute expectation values if you only had access to system A. So the moral is that not observing part of a system is the same as having incomplete information, which is the same as having a mixed state. And this is the origin of the notion of the collapse of the wave function. What do I mean by that? So let's go and revisit the basic postulates of quantum mechanics for a minute. So the collapse postulate of quantum mechanics is the statement that upon measurement, the state of a system evolves from pure to mixed. More precisely, if we are in a state psi, and we measure A, some observable, then we are in a state which is an eigenstate of A after the measurement with a probability that is the square of the overlap between A and psi. Okay. So let's think about that statement for a second. The statement is that we started out in a pure state, And when we perform a measurement, we evolve to a mixed state. And what is the mixed state? Well, it's the state where, with a certain probability, we're in a given state A. That is described by the density matrix, which is the sum over the eigenstates of the operator A of that probability times the projection operator onto that eigenstate. So, one of the reasons why I've introduced for you the language of density matrices is that it allows us to formulate somewhat more precisely the collapse postulate of quantum mechanics. The collapse postulate is the statement that a pure state evolves to a mixed state upon measurement. And this violates unitarity. Unitary time evolution takes pure states to pure states. The state psi at some initial time t will evolve to the state psi at some later time t. And so the density matrix that projects you onto the state psi at time 0 evolves to the pure state density matrix that projects you to the state psi at time t. So the collapse postulate, and this is what we've said before, slightly less systematically, is in tension, I would say, with the other postulates of quantum mechanics. It requires a pure state to evolve to a mixed state in a way that is not consistent with our usual notion of unitary time evolution. However, I have just introduced to you, not 10 minutes ago, a mechanism by which pure states can appear mixed if we fail to account for all of the parts of the system. And this puzzle, introduced by the collapse postulate, is resolved if we keep track of all entanglements. What do I mean by that? Let's consider more precisely what we would do when we perform the measurement of a quantum system. So I will denote by psi the state of the system under consideration, and I will also keep track of the quantum mechanical variables describing my measuring apparatus. So E will denote the state of a measuring apparatus. So, for example, under measurement, if you start with psi in an eigenstate of my observable A, then the state of the system, which is the state of the initial system that we're observing, and the state of the measuring apparatus in some initial state, will evolve to A times some other state of the measuring apparatus, where E sub A is the state of the apparatus after measuring the result A. For example, if EA is some sort of, some oscilloscope, then I could set it up so that one light on the oscilloscope would blink when the state is in a spin up, and another light would blink when the state is in a spin down. I would call those E sub up and E sub down, for example. If A here were the spin of a particle, in the z direction. Okay. Now, measurement is supposed to be a unitary process, and Hilbert spaces are linear. So if we take a generic initial state of the system, and we write it in terms of this basis of eigenstates, then by linearity, if the measurement process is unitary, and it takes A times E to A times EA, then we know exactly what it does to psi. Then the measurement process will take psi to the sum over A times this overlap A psi times A EA. Okay. Now let us imagine the following. So all I've done is I've coupled my quantum system to some measuring apparatus, and I've used the fact that time evolution is unitary and linear, and now let us make the following decision. Let us decide that we don't wish to study the quantum states of our measuring apparatus. Then what does that mean? That means we must trace over the Hilbert space of our apparatus. So that means that upon measurement, the pure state of the system, namely this projection operator, will evolve to the density matrix that is given by the trace over E of the state that I wrote down above. So what is that? That's the sum over A psi, times A EA, times its dual, which is the sum over A prime, times psi A prime, A prime EA prime, which is not necessarily a pure state. So now let me make one assumption about my measuring apparatus. Let us assume that my measuring apparatus is described by a Hilbert space such that if you obtain different results for measurements on the measuring apparatus, then the states are orthogonal. In the case of my oscilloscope with two different lights that could blink, one if the spin is up, one if the spin is down, I'm assuming that the state of the oscilloscope where spin 1 is blinking is orthogonal to the one where spin 2 is blinking. Then what is that state that I have described above? Well, it is the state where we trace over E of EA, the outer product of EA with EA prime, where EA and EA prime are orthogonal unless A is equal to A prime. So that trace will set A equals to A prime, and what will you get? Well, if you just write this as a sum over A, it will be the absolute value of the overlap of A with psi, because of this is the complex conjugate of that, times the projection operator onto A. So what does this mean? Well, this density matrix that I have written here is exactly what you expect by the collapse of the wave function postulate of quantum mechanics. So what we have seen is that by choosing not to measure E, we have reproduced the supposed collapse of the wave function, or I should say the apparent collapse of the wave function. But we have done so in a completely unitary way. That means that there's a slightly different way of thinking about measurements in quantum mechanics. And in particular, if you think about it, you could certainly regard quantum evolution and quantum measurement as the statement that wave functions never collapse. They just get entangled with other systems. They just evolve. And in doing so, they get entangled. It's only when we choose not to measure certain things by, for example, forgetting about the quantum degrees of freedom of the measuring apparatus, that they appear to collapse. We only obtain the collapse of the wave function postulate when you force a sort of classical intuition on a quantum world. If you refuse to think about the entanglement between the measuring apparatus and that of the state that is being measured, then you will inevitably conclude that the wave function has collapsed and that a definite quantum state has evolved in a way that is not completely deterministic. If, however, you keep track of the entanglements between the measuring apparatus and the object being studied, then you will conclude that quantum mechanics is completely deterministic. Let me say this a different way. If you are observing a particle in a laboratory and you observe that its wave function collapses, that is just the statement that your wave function has become entangled with the particle. If you try and use classical dynamics intuition in order to describe that, then you will conclude that the wave function of the particle is collapsed. But that is just because you are uncomfortable about thinking about your own wave function. When you open up the box containing Schrodinger's cat, the cat is still neither alive nor dead. Your wave function has just been entangled with that of the cat. And your wave function is then in a superposition of two states. One is the state where the cat is alive and you are happy, assuming you like cats. And the other is the state where the cat is dead and you are sad, assuming you like cats. I should make one final point here, which is that the assumption that I made here that was crucial was that the basis of states describing our measuring apparatus was diagonal. And that is the statement, essentially, that our measuring apparatus is, in some vague, imprecise sense, classical. And the question that we would ask, then, is why are some variables classical in the sense that the Hilbert spaces are approximately diagonal and some are not. Why is it the case that the overlap between the state where I'm happy because the cat is alive and my state where I'm sad because the cat is dead, why are those approximately orthogonal states in the Hilbert space that describes my quantum system? Of course, they're not going to be completely exactly orthogonal states, so I should really say that this is some squiggly equals, not an exact equals. But they should be approximately equals to the extent that I can be described as a classical macroscopic object. And in trying to understand the distinction between those variables which can effectively be regarded as classical and those which cannot, we're required to think very, very carefully about to what extent and to what approximation this assumption that the Hilbert space for different observables is approximately diagonal is true. And this is a very deep and difficult question. There's an entire field of physics, or of quantum mechanics, known as measurement theory, where people try and answer this question. It's beyond the scope of what I want to discuss today. But I did just want to introduce and spend some time thinking about entanglement so that you could see that there's a way of thinking about it where the collapse of the wave function is really not a separate assumption about the rules of quantum mechanics, but rather it is a statement about the unitarity and linearity of quantum evolution, along with this assumption about those variables that we choose to regard as classical. Now, the picture that I have introduced, where wave functions do not collapse, they simply evolve, sometimes has very fancy words attached to it, things like the many worlds interpretation of quantum mechanics, the consistent histories interpretation of quantum mechanics. Those words, I think, make a much bigger deal out of this than is necessary. From my point of view, interpretations of quantum mechanics are really not important because they don't change the outcome of measurement. They don't change the outcome of experiment. So if you wish to regard the collapse of the wave function postulate as correct, then you are free to do so. It's not going to change the outcome of any measurement or experiment or any prediction of the theory of quantum mechanics. However, I think it is important to note that the internal logic of quantum mechanics is completely self-consistent without the assumption of the collapse of the wave function. And all that it requires is a bit of generosity on your part, where you accept the fact that observers and experimental apparatus are as subject to the laws of quantum mechanics as anything else. Okay. It is not the job of quantum mechanics to fit with our classical intuition. It is our job as physicists to modify our classical intuition so that we can better understand quantum mechanics. Sorry, I've gone over time by a few minutes. I do have time for maybe one question. I don't really, but I'll take that time anyway. Okay. I will see you guys on Wednesday.